Thank you so much. Thank you, Sasa and Zainab, for the invitation. Thank you all for being here. So today I'll try to explain a simple idea for mathematical modeling, which is how some non-equilibrium effects can basically help us obtain and control stable complex steady states. I'll explain all of these terms as I go through. Okay, so all right. So usually as so usually as we develop mathematical models, we tend to think about equilibrium. We like to see how the system goes to a rest state, basically. Okay, and as mathematicians, this equilibrium state is characterized by an energy minimization. So if I'm trying to develop a model, I'll come up with a free energy, and I will say if I minimize, I'll have to develop my model such that if I minimize this energy, I'll find my equilibrium state. Okay, and this is attractive because it's consistent with the physics. That's what the second law of thermodynamics says, right? And the important thing to observe here is that when you see a PDE model, it doesn't describe the state of the system. It doesn't tell you this is equilibrium or non-equilibrium. It tells you how the system flows from a state to another one. Okay, so that's how you derive your fluxes and other effects. It tells you how your system will travel from out of equilibrium to an equilibrium state. And we can basically explain this with a simple diffusion equation. So consider you have a mass density in a certain domain that is diffusing. All right. Let's say that your mass is conserved, which is given by this law. This basically says that your mass evolves according to its flux, right? And I have a no flux boundary condition, and I'll choose the usual directly free energy for this system. Okay. So all I need to do is find out what's the flux, and I'll close my system. How should that be chosen? As I said, we want to go towards equilibrium, which is characterized by energy minimization. So I'll choose the flux such that my solution will minimize the energy. What I want to do now, I will vary the energy. Okay, so I know how does it change. I will get something called the chemical potential. That's basically the energy cost of adding one molecule to the system. And that cost will tell me where to flow. I will basically flow against that cost. I'll go from high cost to cheap cost. That will be my flux here. Okay. You have to pay attention here that this gradient of the chemical potential is a force, right? And that D is basically my diffusion coefficient. And what this says is that the diffusion coefficient tells me how easy it is for this flux to drive, for this force to drive that flux. Okay? I close my system and I get my diffusion equation. All right? And from the way I derived this equation, it's guaranteed that the energy I chose will decrease. Let's check that. Okay, so you can think of maybe, I don't know, like a drop of food coloring in water, and it starts diffusing. And you can see as the mass is diffusing, the energy is going down. We are going towards an equilibrium state. All right. So all of this is great, and it seems like an effective yet simple framework. Let's try it with something else. Let me introduce you to something called lipid rafts. So lipid rafts, so if you think of cell membranes, they're not uniform in composition, so they have different compositions. One thing you can think about is saturated lipids and unsaturated lipids. So specifically the saturated lipids, they like to cluster and group together, so they form small domains, microdomains. Those domains are called rafts, okay? And there's an important thing which we'll come to later if I have time, which is this cholesterol, which likes to stay inside the raft domains, okay? So how do I model this? From the diffusion equation, we started with something that we want to track. We started with the mass density. So I need to create something that I need to track. In this case, I will introduce an order parameter. Because I have two phases, this phi would be basically like an indicator. If phi equals 1, I know I'm in a raft region. If phi equals -1, I know I'm in a non-raft region, okay? And I'll do the same thing, the same exercise. I will assume my mass is conserved, okay? I have a flux that I need to derive. The flux will be related to this force, which is the gradient of a chemical potential. The chemical potential will be derived from the variation of an energy, okay? And one thing I need to emphasize again, this is a force, and that m is mobility constant. Again, it tells me how easy it is for this force to drive that flux, all right? So I need to find the energy now that I will need to vary. How do I do that? So first of all, I want phi to be either 1 or -1. And at the same time, I want to go to equilibrium by minimizing an energy. So I will set up my energy such that it's minimized at -1 and 1. This is a double well energy. So you see, these are the minimums for this energy density. Okay? Now, when my model or the system phase separates like this, so I have -1 and 1, I would expect a transition between. Okay? I'm afraid that the transition would be so sharp that it develops its instability in my system. So I need to penalize high gradient values. And that's what I do. Okay? I add the penalization term to the energy, penalize high gradient values. Now, because of this transition, I want some flexibility to control how smooth or how sharp I go. I'll add another parameter, epsilon. And as you can see, if I make epsilon smaller, I'm weakening the penalization of the gradient, and I am strengthening the phase separation from -1 to 1. Okay? So if I choose epsilon smaller, I get a sharper transition from -1 to 1. This is a 1D example. This is known as the Ginzburg-Landau energy, and the variation of this is very famous. It gives me the Cahn-Hilliard equation. Okay? If I do the variation, get the flux, feed it to my mass conservation, I get the Cahn-Hilliard equation. So what does this do? Two things. It tries to phase separate the components of the system while conserving the mass and going towards equilibrium, because that's how I derived it. Okay? So I want to test this and see if it gives me the rafts that I want. So nice domains then. The domains start merging. And basically this SPAAM, you can see the energy is decreasing. At some point it will flatten. I know I've reached my equilibrium. Okay? But there is a problem here, which is if I discuss the scales of the model here, it will be evident that these are too large to be considered rafts. Okay? I need something very small. So why didn't this framework work at this time? It's because that's how I design it. There is nothing stopping the phase separation. So all I did is that I said that I want my model to phase separate and go towards equilibrium. Why would it not merge all the domains together? Okay, so there is something missing here. So even if I show you the rate of change of the energy, right, and I use my energy, take time derivative, I'll use integration by parts here. Because I have a no-flux boundary condition, I get rid of all the boundary terms, and my mu, my chemical potential, appears again. Using integration by parts again, the force appears again. Okay, so it's evident that it is the force with the mobility constant that is driving the decrease of the energy. Okay, so the idea is, what if I can introduce something that will compete to this force? Okay, instead of trying to merge all the domains, I will try to introduce something that will try to, provide these complex little domains for me. Before we discuss this, let me give you another example of how we would derive such a thing. Assume you own a dance floor, okay? And you have two kinds of people dancing on that. Let's say red dancers and blue dancers. And let's assume that the red dancers like to group together so they can maybe dance together, okay? Two things can happen here. If you just let them be, right? Eventually, they will all group together and that the system will stay at that point, okay? The second choice is that if you want, or if you you can basically keep removing people from the dance floor and putting them randomly somewhere else. Okay, so if you see red dancers trying to group, you take someone and randomly throw them somewhere else. Okay. As time goes, the overall behavior will be that they can only form smaller groups, because each time they try to grow, you will take someone away and throw it somewhere else. Okay? So maybe I need an exchange like this in my system. And this would be a great point to explain what's equilibrium and what's steady state. So the dynamics that I explained before from the diffusion and the Cantor equation, in this example is that the red dancers like to cluster. This is the dynamics of the system. This is how the system evolves. Okay? Now, if I don't do anything, I'll get to an equilibrium state, like the energy I showed before. All right? But if I introduce some kind of an exchange, that exchange over time it will balance, and that will give you a steady state. This is the difference between an equilibrium state and a steady state. All right? Okay, let's do this. Let's start to my model. I will add a mass exchange to my Cantor equation. So you see, I have my Cantor equation the same, and I added this blue term here. This blue term is just an exchange of mass. What it does is that it tries to balance the amount of mass I have against some constant phi bar. Okay, and K is how fast I can do that. So I have two parameters now. How fast I can change the mass and how fast I can transport the mass, which is M. Okay? So what would this do to the model? Let's see another simulation now. So again, I get those smaller domains. Will they stop or merge? They start. Okay, it's better than the previous one. And you can see what the reaction term does do to the energy. It increases the energy at the beginning, then it lets it go down. You see, this state here, it's not an equilibrium state, it's a steady state. This is the difference. I still have the exchange of mass, it's just balanced at this point. That reaction term, we call it a non-equilibrium. Why? Because it disturbs the journey of the energy towards equilibrium. Okay, which is this increase here. If I take you back to the energy rate of change, you can see that apparently really. So in the last slide, we had only this term. Now I have the blue term appearing as well, and I can't always guarantee that this is negative. Okay, so the energy doesn't decrease monotonically. And you can see there is some kind of a competition here between the dynamics that tries to phase separate the system and the dynamics that tries to exchange mass. So what's really happening here is that the red term, which tries to drive phase separation, is trying to go towards equilibrium, reduce the mass, and reduce the energy. And the blue term is trying to exchange mass, providing an active process basically in the system and increasing the energy. When they balance, they meet at steady state, which is what we saw in the plot of the energy. Okay? And the two parameters that I showed you or told you about before, M and K, are what controls the dynamics. So if I try, for example, if I try to keep K constant and lower M, we'll see what happens, and keep that lower M, then lower K again. I'll play the two videos and you can observe what happens. So you see, as I lower M, the tendency of the system to phase separate completely, I get even smaller domains because the reaction term is too strong for it. Okay. Now, if I lower the rate of change, of mass exchange, I will get the larger domains again. All right. So this is how M and K, only M and K in the model here, control the size of those rafts. Okay, now the last thing I want to explain is that cholesterol that I told you about. So I told you that the cholesterol likes to stay in raft domains. In fact, it has an affinity towards raft domains. So even if it's outside, it will try to diffuse towards these raft domains. Okay, let's try to provide a model for this with tweaking the previous model. Let's see. So I'll keep the same energy, and I would add a term here. This is a coupling term. What this term tries to do, it tries to force W to be like 1 plus phi over 2. So if you see, if I have phi equals 1, I get W equals 1, right? So W equals 1 in raft regions. If I have phi equals minus 1, I get W equals 0. So W is not present in non-raft regions, okay? And the assumption here is that instead of adding a mass exchange for phi, I will add a mass exchange for W, for the cholesterol. So remember, I said that the reaction term, which is the mass exchange, will cause non-equilibrium in the system. But this time, non-equilibrium is coming from W, not from phi. What do you expect would happen? Let me show you the video. So I get those smaller domains again. Although I didn't introduce a non-equilibrium effect to phi, I still get the same behavior. And that's because, also, if you look at the rate of change of the energy, it's the same story. I have two forces, this one and that one. Both are the dynamics of W and phi trying to reduce the energy, but I have one single term, which is the reaction coming from W, trying to fight this decrease, okay? So the idea here is that whenever you think about equilibrium and non-equilibrium, try to think about it at the systems level, not at the level of the components. So as long as phi and W are coupled, if W has a non-equilibrium effect associated with it, that will be transmitted towards phi, okay? And the same behavior will happen. All right? So just to recap, what have we learned today? So we learned that mathematical models usually describe the evolution towards equilibrium. They don't describe states, right? And that's note to self to me that non-equilibrium is not bad after all. So when I started learning about this stuff, I always thought that non-equilibrium is not that great because it makes my energy increase. But then apparently that could be nice. Why? Because it also helps us model some complex systems, like the rafts in this case. And the last thing is that whenever you think about equilibrium and non-equilibrium, try to think of the system, not of the components themselves. Okay, thanks so much.
Questions? Thank you so much for the great talk. No questions?
So is your cholesterol a third species occupying space, or is it just kind of, if you're thinking of this in terms of lipids, is that taking up surface area as well, or is it kind of?
No, it's not taking surface area, this case, yeah, so.
It's just reacting with the.
There is no volume exclusion conditions here, or area exclusion if you think about surface.
Any other questions?
Yes?
So in the not latter two, but like the middle two simulations you showed, the energy decrease was like sort of stepping.
Yes.
Why is that?
It's because the domains were merging. So if you notice, as the domains merge, the energy decreased. Okay, and let me go back to that one. Was it this one? Yes. So when the domains are merging or disappearing, the energy decreases because that's what the system wants, right? It wants to gather everything at once, right?
And so it was smooth in the first case because you had that just all coming into one block.
Yeah, definitely. Yeah.
More questions? No? Thank you so much again.
Thank you.